Hello, everybody, and welcome to our video on more derivatives of trigonometric functions. Just as a quick summary, remember that the derivative of sine x is cosine x, the derivative of cosine x is negative sine x, and as we saw in some examples, you can derive this, but the derivative of tan x is 1 over cos squared x, which could also be called secant squared x, because this is a reciprocal function. Okay. And then if we have to use the chain rule, if we are taking sine of a function or cos of a function, remember that we have to do the derivative of the outside part times the derivative of the inside part. Okay, so let's see some examples. So for this one here, for y equals sine of x over 2 minus 3 cos x, I take the derivative of the outside part, which is cosine of x over 2, times the derivative of the inside part, which is 1/2, and I'm going to subtract. I'm going to pull out 3. I'm going to take the derivative of cosine x, which is negative sine x, and I'm going to tidy it up a little bit. Match my signs up here, bring the factors in front, that sort of thing. Okay, and I can leave it in that form for now. There's not really much I can do after that. For this one, we have a derivative with tan. Remember to pull that 3 out first. Take the derivative of tan, which is 1 over cos squared of what I'm taking tan of, times the derivative of pi x. Remember that x is the thing I'm taking the derivative of. Pi is just the constant. And so that is pi. And then I multiply it all together to give me 3 pi over cos squared pi x. For number 2, we have a couple of functions here to work with. Again, a combination of lns and sines. So just a little bit more complex. Remember that this is a chain rule question. I need to take the derivative of the outside function times the derivative of the inside function. So remember the derivative of ln is 1 over whatever you're taking ln of, and the derivative of the inside part is cosine x. So I get cosine x over sine x. That's also sometimes called cotangent x or 1 over tan x. So this, or this are all possible answers. For L, we have 8 over tan cubed of x over 2, so we're just getting a little more complicated. It might help if we rewrite this as a product instead of as a quotient. So 8 times tan of x over 2 to the negative 3. Then I can pull out the 8, drop the 3, keep the tan x over 2, reduce the exponent by 1, so that becomes negative 4. I know that's a little weird to see. Times the derivative of the inside, which is 1 over cos squared x over 2 times 1/2. And then I can tidy it up a bit. 8 times 1/2, that gives me the 4, times negative 3 gives me this negative 12. In my denominator, I have a tan of x over 2 to the 4, and a cos squared of x over 2 all squared. Okay, now your book stops here, but if you wanted to follow some extra steps, okay, you could rewrite tan as sine over cosine and see if you can kind of cancel out some common factors. Okay, last, a little more complex problem. A function is defined here. Write down the expression for f of x in the form k times sine 4x and solve f prime of x equals 0. So for the first part, remember that sine 2x cos 2x is a version of this sine double angle formula. So I could replace this with, it's like these x's here are replaced with 2x. So sine of 2 times 2x is 2 sine 2x cos 2x. So sine of 4x can be replaced with this expression. Okay? So here this sine 2x cos 2x could be replaced with 2 sine 2x cos 2x. And that's times negative 5. Okay, so I'm kind of replacing, since I'm replacing this part, the 2 and the negative 5 multiply together to give me that negative 10. And so this becomes sine 4x. Then if I want to solve it, that's going to use some of the tricks we've used over the past few days. Okay, I'm going to take the derivative, so pull out the negative 5, take the derivative of sine of 4x, which is cos 4x times 4, multiply, and simplify. I'm going to get 0 equals 4x. Now this is a bit more complicated, so we're going to see here that this has a horizontal compression of y equals cosine x. So if there's 2 times when y equals 0 for y equals cosine x, there's 4 times as many times that on that new function. Okay, so we find